All right, everyone, we are on to our second problem, which is all about dynamics. So we have a 12-meter long beam, and we know that this beam has this moment of inertia, some IG, and we have a center of mass or centroid at G, which is going to be basically half the length, so about 6 meters. The beam is 100 kilograms. Center mass is where the weight is applied, so we have some weight as well. Calculate linear acceleration and angular acceleration of the beam. So it's hovering just above the surface, so basically it's like just touching. But we're basically not going to deal with any friction in this problem. That's what that sentence means. So we have XY coordinate system, as usual. We're going to free the body, FBD, free the body from the diagram, and we're going to have right here, there's going to be a weight, and our weight is going to be mg. We're also going to have basically the force here, which there's going to be a component in the x. So in this triangle here, our x component is going to be 200 times cosine of 60 degrees. So that's going to be our x component. So force here. We're also going to have a force in the y, which is going to be equal to, I'm going to put it here, 200 times sine of 60 degrees. And we also have a force here that is 100 newtons in this direction. So that's our free body diagram. We also have a kinetic body diagram. And when we are dealing with this here, so once we pull or start to pull this, we're going to have some acceleration in the y. We're probably going to have like some acceleration in the x perhaps. And we're also going to have some rotational component as well. So when we pull up and kind of to the side here, perhaps we have some rotation, some alpha as such. So free body diagram, kinetic body diagram, some of the forces in the x must be equal to the mass times the acceleration in the x, which is going to be equal in this instance to just 200 times cosine of 60 degrees. Some of the forces in the y equals mass times acceleration in the y, which are going to be equal to 100 newtons plus 200 newtons times times sine of 60 degrees minus w. And we're going to have some, and I'm going to actually take, let's go ahead. How should we approach this? I'm going to take the moments. I'm going to do the moments about G, which is just going to be our I alpha. I'm going to do the moments about G, and that's going to be equal to the moment, and then is going to be equal to our inertial moments, which is just going to be IG alpha, which must be equal to all the other from the forces. So we can go ahead and solve for those. So the kinetic moments will just be this, and now we need to do, because we're doing it about G, so we don't have to deal with weight, but we will have to, if I want to, I'm just going to play. So if we have this moment here, so our perpendicular distance from the line of action, if we put our finger there to curl in that direction, it's going to be minus 100 newtons times 6, this line of action here. And then we also will have the perpendicular distance from this line of action. We're going to assume that, again, this is going to be basically, there's going to be 0 perpendicular distance from here. So, because it's just crossing through. So for this, there's no like kind of half distance here, so it's passing through. So the perpendicular distance from the line of action would be 0 for this force. So really it's the only other forces here, which is going to be a positive plus, let's go ahead, plus 200 newtons sine of 60 degrees times 6. Because basically the distance here and here. That's our perpendicular distance from our line of action. So let's go ahead. Let's calculate that. I'm going to quit the kernel. We have, what's our mass? 100 kilograms. So mass is equal to 100. G is equal to 9.8. weight equals m times g, and we can go ahead and get started. We also have the mass moment of inertia is the length, which is 12 kilogram beam, or 12 meter beam. Ig equals mass times 12 squared, all that divided by 12. All right, then we can zoom out one more time because we've got everything else we need. So the kinetic moments about that point G, we're just going to have that rotation. And finally, let's go ahead and solve. So Fx equals mass times, or m times ax, equals 200 times cosine of 60 degree. And then we have Fy equals m times ay equals 100 plus 200 times sine of 60 degree. And then finally we have mg, which is equal to ig times alpha, which is equal to minus 100 times 6 plus 200 times sine of 60 degree times 6. So let's go ahead and look at how this runs. And then I'm going to solve fx, fy, mg. Oops. Let's solve this numerically. And we have a solution. So that is pretty much what we've got. So we will see you all in the next video. Or actually, for our problem 3. So thanks, and we'll see you then. Bye.